Today I'll talk about my recent joint work with Chen, and Yu Guang. The title is Incompressible Hypersurface Particle Curvature and Polymath Theorem. The main work we done is to generalize Riemannian polymath theorem for manifolds whose end have more complicated topology. So I'll start from the polymath theorem, and I'll start with a very rough motivation for polymath theorem. The motivation for polymath theorem comes from general relativity, and unlike in Newtonian mechanics, in general relativity, the mass curves the space, so it is a basic but important problem to decide how to quantify the mass containing a spatial region from the bending of the space. Searching for suitable definition of mass and showing its non-negativity under reasonable condition just motivates the research on polymath theorems. And the classical Riemannian polymath theorem deal with this problem in a simple case. In this case, the Euclidean space is taken as vacuum space, and the isolated gravity system is modeled by asymptotically flat manifolds. And a asymptotically flat manifold is a complete Riemannian manifold with dimension no less than 3, and such that outside a large compact subset, there are only finitely many ends, and each end is diffeomorphic to the Euclidean minus a ball, and the metric approaches the Euclidean metric at infinity. And for a well-defined mass, we needed to put additional requirements. We needed to require the difference between G and the Euclidean metric should decay in some suitable order. And we also require the scalar curvature to be integrable. And there is a model for single black hole, and it is Schwarzschild manifold. And it is conformal to the Euclidean space minus the origin. And there is a parameter A in the conformal factor, which is required to be positive to ensure the complete of the manifold. From the expression, it is quick to see it satisfies the decay condition too. And also, Schwarzschild manifold has vanishing scalar curvature, so it also satisfies the condition 3. So it is an asymptotically flat manifold. And for each asymptotically flat end, there is a well-defined ADM mass raised by Anowitz, Stans, and Mitzer. It is given by the following flux integral on infinite sphere. Here, the coefficient before the limit is slightly different. We just take this coefficient for simplicity. And it doesn't matter when we just care about the non-negativity of the ADM mass. Now, for the simple example, Schwarzschild manifold, we can calculate that the ADM mass equals to 4n minus 1a, which is positive. Now we can state the Riemannian polymath theorem. It is proven by Xiong in a series of work, and Witten for the spin case. The Riemannian polymath theorem says if Mg is an asymptotically flat manifold with non-negative scalar curvature, and E is one of its asymptotically flat ends, then we know the ADM mass of this end should be non-negative. Where the mass vanishes, if found only if the manifold Mg itself is isometric to the Euclidean space. And from the statement of Riemannian polymath theorem, you can see there is only one end involved in the statement, so it's natural to think about the. It is natural to ask whether we don't require we just needed to require one end to be asymptotically flat and other ends just be complete. This is indeed the case. And yes, the right picture is just showing the so-called asymptotically flat manifold with arbitrary ends. Namely, we only have one asymptotically flat end, and the other ends we don't prescribe the asymptotics. We just need to require them to be complete. And there are several works to this improvement. And I didn't. Yes, I just presented here. Yes, as I mentioned before, the classical Riemann positive mass theorem just deal with the case when the model space is a Euclidean space. So what if the model space have more complicated topology at infinity? For example, the model space is some quotient space of the Euclidean space, model some group actions. There are some trials from along this direction, and I mentioned the Hawking-Pop generalized positive action conjecture. And in this conjecture, they just consider asymptotically locally Euclidean manifold. The definition for such a manifold is similar to asymptotic flat ones, except we require its ends are diffeomorphic to R minus a ball mod some finite group. So here I didn't present the detailed definition. You know, it's only different in the end. And the Hawking-Pop generalized positive action conjecture says a conjecture that any asymptotic locally Euclidean manifold with vanished scalar curves have non-negative ADMS, which vanishes if and only if the manifold is Ricci flat with self-dual curvature. And unfortunately, this conjecture is in general wrong. And LeBron, he can construct for every integer no less than 3. There are counterexamples of Hawking-Pop conjecture asymptotic to R4 quotient ZK. And here, Fk equals 2, LeBron also construct an example, and it is just the Guch-Hansen space. Guch-Hansen space. It is Ricci flat with a vanishing mass. So it is unclear whether there is any counterexamples with its end asymptotic to R4 quotient by Z2. So maybe in this case, the Riemann positive mass theorem can be true. And apart from this, since asymptotically locally Euclidean manifold just has model space, which is Euclidean model some rotational group. You can also think about Euclidean space model the translation group. Namely, you can take the model space to be Rn-1 cross S1. And such manifolds are called asymptotically locally flat manifold. The fact is, positive mass theorem also fails for such manifolds. And the typical example is the resonant Nordstrom manifold, and we will mention this below. From this part of discussion, we know if we would like to make positive mass theorem valid, then we need to add some additional condition. And here I will introduce the positive mass theorems with spin compatible condition. In the ALG case, it is done by Dan. And he required the ALG manifold to be spin with non-negative scalar curvature. And furthermore, the diffeomorphism between M minus K and the model and the end of model space, preserving the spin structure. Namely, if you pull back the spin structure on the model space to m minus k, then it coincides with the given spin structure on M. And if these conditions are satisfied, then he says the mass is non-negative. And with similar condition, Mineberg also established this type of Pauli mass theorem for ALF case. And we don't feel so satisfactory with these results, since first it requires manifold to be spin. And on the other hand, okay, the spin compatible condition is not easy to verify. So our motivation to search for more direct topological condition in the non-spin setting. For example, in the ALG case, if we plot the incompressible condition, namely, if we require the inclusion map between fundamental group of and E to M as injective, then the Riemannian positive mass theorem is valid. This is a simple corollary of the Riemannian positive mass theorem for asymptotically flat manifold with arbitrary N. Since we can always lift the ALE manifold to its universal covering, and its universal covering is asymptotically flat with arbitrary N. Yes, so we want to see whether Riemannian positive mass theorem is valid in the ALF case if we have such incompressible condition. And now I am ready to state our results, but before that, we just make the setting general. Okay, we introduced the asymptotic flat manifold with fiber F, and it's okay. There is only a slight difference in our definition, and that is we require the NE, okay, is diffeomorphic to RD minus a ball cross F. Now here F is just a closed flat manifold, and in our consideration, we always consider manifold with arbitrary N. Namely, we just require one distinguished N to have this kind of asymptotics. And there are several examples in this class. Okay, for example, you can just construct like Schwarzschild manifold. You can take the model metric and you do conformal to construct a family of scalar flat manifold, which is asymptotic flat with fiber F. And we'll call such manifold Schwarzschild-like, since the construction is like Schwarzschild. And you can also take directly product of Schwarzschild manifold with the flat manifold F. And such kind of manifold we will call a Schwarzschild product manifold.
Can I ask a question?
Sure.
The R here, is that only the Euclidean distance, or is that a distance in both parts?
It's only the Euclidean distance.
Thank you.
Yeah. Oh, thank you. Thank you for pointing out, okay, this.
It doesn't matter though, because the condition implies that the two are highly comparable.
Oh yeah.
Thank you.
Yes. And I want to point out that if R is taken to be the Euclidean distance, then the metric constructed is just scalar flat. Yes. If you take the distance to a point, then you will have error. Yeah. And the third family is of interesting. It has the same name, Schwarzschild manifold, but to distinguish this from the one at the beginning, I will call this receive-flat structure manifold, since these manifolds are receive-flat, and it is given by the metric completion of some manifold M bar G bar, where M bar is RD minus the bulk process 1, and the metric is given like this. Yes, here I want to point out that the circle component is 1 in M bar. Finally, can shrink to a point in M. So in this example, I'll say there is a topological loss from the end to the anti-manifold. Okay. And this is related to our statement, so I just point out this fact. And now let us go to the fourth example, the Riemann nostril manifold. It has similar definition as the receive-flat structure manifold. It is also defined to be metric completion of M bar G bar. Here M bar is also R3 minus 4 crosses 1, and the G bar is given like this. And here we just introduce another parameter B. So with this extra parameter, we don't require A to be positive, but only A squared plus B squared to be positive. So in this example, A can be negative. This is the key why such manifold provides counterexample. Also, similarly, the circle component also shrinks to a point in M. So, and this example also has a topological loss from end to the anti-manifold. Yes, with the after introduce a suitable total mass, just like the alien mass, we can calculate that the mass of these manifolds are all a positive multiple of A. So as we mentioned before, in the fourth example, A can be negative. So its total mass can be negative. And then recall that we mentioned the Riemann nostrum provides counterexample to Riemann party mass theorem for AF manifold. Okay, here we just explain the reason.
Can you show the metric
sure.
for the Reisner-Nordstrom one again?
Yeah.
It's just nice to look at it for a while.
Okay. When B is 0, it just go back to the receive-flat structured manifold. And the perturbation is, you can, when B is small, you can think this metric as a perturbation of the receive-flat structured metric. And the perturbation is done in higher order.
And
so it's,
do you call it Ricci flat because this metric is Ricci flat, or because there's an associated space-time metric that's Ricci flat?
This metric, in the third example, the metric G bar is Ricci flat.
Okay.
Yeah. And in the space-time, if you put here the minus sign, it does not affect the Ricci flatness. So what you say is here put a minus, so it will be a space-time. Yeah. So if we change the minus sign to positive sign, plus sign, then it is still Ricci flat, and this is a Riemann manifold, not a Lorentz manifold. Okay.
And the other thing is, in number 4, is that a complete manifold? I mean, is that a complete manifold without boundary in the end, or do you take out a large section, a compact section near the origin? So this looks like an end of a manifold.
Oh yeah. So if you take the metric completion, then MG is a complete manifold.
Yeah, but what I mean is then it has an inner boundary, right? It's not a an
No, it does not have an inner boundary. It's just like if if you want me to describe, it's a kind of you look at the two neighborhood of Clifford torus in S3, for example, then when you near the bound, it will eventually close. I mean, let me say.
Look, it's defined on a manifold that has two ends. So when you're finished, does it only have one end and the inner one has become compactified?
Oh, yeah, yes.
Okay.
Yes.
So it's a manifold without boundary that's complete, and it violates the positive mass theorem. That's all I wanted to know. Yeah. That's the case. So our theorem just put some condition, I would say incompressible condition to forbid the topological loss from end to the anti-manifold. So we can rule out the conic example, this first conic example. Yeah, so the statement is like this: FMGE is asymptotically flat manifold with fiber F with non-negative scalar curvature, and one of the following holds. If for general fiber, we know the inclusion map from the fundamental group of the end to the fundamental of the anti-manifold is injected, or the fiber is S1, we just require the inclusion map to be non-zero. Okay, if one of these two holds, then we know the total mass is non-negative. And in the first case, yes, we also have the rigidity statement. In the first case, if the total mass vanishes, then the manifold MG must be flat. In the second case, if we require the matrix further satisfy a decay condition to the third order, then the total mass vanishes yields that the manifold splits as RD across S1. We believe, the condition one is technical, but we don't know how to get rid of that.
So the dimension injection is because you use like minimum surface method?
Yes. Let me see. Yes.
Thank you.
And as I mentioned, the requirement went on to just rule out the topological loss, so it's rule out the Ricci-flat Schwarzschild manifold. Although the Ricci-flat Schwarzschild manifold has positive mass, we don't see this fact from our Riemannian positive mass theorem. But I mentioned that Miller has one version of positive mass theorem for manifold with non-negative Ricci curvature. Yes, in his setting, the Ricci-flat Schwarzschild manifold is allowed, but the definition of mass is slightly different. I just mentioned the remark here. Yes, apart from this positive mass theorem, we also consider the Cone-angle estimate, which is a 2D analogy of PMT. In this setting, we consider asymptotic conical manifold with fiber F. Now, the n is diffeomorphic to R2 minus 4 cross F, and the metric on R2 we are chosen to be some conical metric. And the constant 2 pi beta will be called the cone-angle at infinity. And if the dimension of if Mg is just an asymptotically conical manifold in 2 dimensions, and the Gaussian curvature is non-negative, then the Gauss-Bonnet formula just yields that the cone-angle cannot exceed 2 pi. And we establish a similar result for asymptotically conical manifold with fiber F. Of course, yes, here I just mentioned the 3-dimensional case. It says FMGE is an asymptotic conical manifold with fiber S1, such that the scalar curvature is non-negative and the inclusion map is non-zero. Equivalently, that says the fiber does not shrink to a point in this manifold. Then the angle of this manifold, the cone-angle of this manifold at infinity is no greater than 2 pi. And the equality just implies Mg is flat. And the strategy to prove these 2 theorems is classified as low-camp compactification. And the philosophy is like this. It says that if the model space can be sealed into a closed manifold, can be sealed into a closed manifold, then the polymetric could be reduced to a topological obstruction problem for p-asymmetric on certain manifold. Yes, in our case, our model space is Rn cross Tk. So if you take a large cube in Rn and identify its opposite faces, we can seal the model space into a closed manifold. And we can use these facts to reduce PMT to some PSC obstruction problem on manifold. Okay, the way is we will argue by contradiction. We will deal with when the mass is negative. In this case, we try to increase the scalar curvature inside and deform the infinity to model space meanwhile. And in this case, we can just seal the manifold. And then now we just need to rule out p-asymmetric on the manifold after seal. And for asymptotically flat manifold, this just reduced to manifold like Tn connected some with some manifold. And here, since we have extra fiber Tk, so we will deal with manifold from generalized connected sum. So next time I'll talk about PSC obstruction problem on manifolds from generalized connected sum. The setting is like this. We just fix sigma to be a closed manifold, and we consider those manifold M associated with an embedding from sigma to M with trivial normal bundle. And here we don't require M to be compact. And if we have 2 such manifold M1 and M2, just look at this picture. If the image of sigma in M1 is sigma 1, and the image of sigma in M2 is sigma 2, we just take away the tuple neighborhood of sigma 1 and sigma 2, then glue in the rest part along the boundary. And this is what generalized connected sum means. And there are already several work on the relation between polyscalar curvature and the generalized connected sum. And okay, there are 2 properties. Okay, the first property is PSC preserving property. It's proven by Xiong Gromov-Lawson. And it states that if we have 2 manifolds, both admit complete PSC matrix, and sigma has codimension at least 3, then the generalized connected sum also admits complete PSE matrix. Yes, on the other hand, we also have overstructuring preserving property. Yes, and it states that if sigma is a point, then if sigma is a point, then this is just the classical connected sum. Okay, we have Tn doing connected sum with some manifold M cannot admit any complete PSE matrix. But the obstruction preserving property, yes, does not hold for generalized connected sum in general. For example, the manifold, we just take 3 torus and 3 sphere and doing the generalized connected sum along sum S1, then the manifold obtained actually admits PSE matrix. And this fact can be shown using Miao's technique. Miao says if you glue in 2 parts along the boundary, yes, then the scalar curvature at the corner is positive or not. It's totally decided by the mean curvature on 2 sides. Then and we have the following observation. If we just take the product metric on, we take a flat metric on P2 minus B, and we consider product with S1, then the length of the second circle component does not affect the mean curvature. While if we take the product of S1 and flat disk B, then the length of the boundary of B affects the mean curvature. We can take the length of a second circle component to be small enough so that this part has very positive mean curvature. Then we doing the gluing, and the Miao's argument tells us such manifold will have positive scalar curvature in the distribution sense, and we can do a conformal so that construct a smooth positive scalar curvature matrix on such manifold. So the fact is that obstruction preserving property does not hold in general. So it's natural to ask what kind of generalized connected sum would have obstruction preserving property. And for our reduction, we just consider one of the manifold is Tn, and the sigma is just a subtorus Tk in Tn.
Sorry, Jintian. So the previous result of the connected sum, there is a dimension restriction. I mean, this traditionally result.
Because they have to use bubble, so I for safety. So they have the dimension restriction.
Yeah.
It's the same, right? It's from the possible singularity for area minimizing things.
Okay. But I think this can be proved by index theory method, even
oh
if
yeah.
M
So
is not spin.
you may, yes. You say if M is not spin, you can still prove this.
Yeah, by some kind of partial index. I'm pretty sure.
Oh, I didn't know that. If this true, then
No, I don't know if that's in the literature. Yeah, but well, at least in my mind.
Oh, sure. And if this is true, then of course there's no dimension restriction to this result.
Okay. Yeah. Thank you.
Yeah, and what we find is if you require sigma embedded to n. Okay, if the fundamental group of sigma embedded to that of m injectively, then the generalized connected sum does not admit any complete metric with partial scalar curvature. And moreover, any non-negative scalar curvature metric will be flat. And since we doing generalized connected sum, actually we just need the inclusion map from pi1 sigma to pi1 m minus sigma is injected. Okay, here we just abuse the notion. Okay, here pi1 sigma we just perturbate sigma a little bit. Since sigma has trivial bundle, so we can push it away from the original position a little bit. Now the new surface will in m minus sigma. So what we mean is the fundamental group of the perturbated surface embedded to pi1 m minus sigma is injected. Yeah. So here we don't know. Okay, currently we don't know whether here m1 taken to be torus is necessary. Maybe you have a larger class of manifold and you're doing some incompressible generalized connected sum. It's still preserving the abstraction for partial scalar curvature metric.
Wait, can I make a comment here?
Yeah.
So I think in this case, if you assume spin, then this is basically a codimension 2 index phenomena, the injectivity. That's essentially what's done before. So yeah, if you assume spin, this would be a
assume m to be spin.
Yes, if you assume everything to be spin, yes.
Oh, I didn't know that. Thanks for a comment. So do you have the same phenomenon just like this? I just mentioned. Okay,
Well,
you just need one.
I mean, for this theorem, if you know spin, then that follows from the work of Gromov-Lawson in the previous theorem, right?
Oh yeah.
The previous theorem, if you assume spin, then that's because of enlargeability of torus. There will be no dimension restriction.
Oh yeah. Yeah. This is where our proof wrong. Yeah, I will mention that later. Our proof for such theorem just comes from Gromov-Lawson's work. Yeah, I'll mention that. And then if sigma is S1, then we can relax the condition. We just need to require the inclusion map is non-zero. Yes, and similarly, we just need pi1 S1 to pi1 m minus S1 non-zero. Yes, and the reason why such theorem holds is due to this, because the generalized connected sum does not affect the topological condition on certain hypersurface. Although it changes the topology of the manifold, but it does not change the information of certain hypersurface. And in the first case, if the TK is yes, if pi1 TK to pi1 m is injected, then we know the shadowless hypersurface, namely this Tm minus k minus 1 cross TK is incompressible. Yes, which means the fundamental group embedded to the whole space is injected. It's okay. It's you can see this very clearly, right? The last p circle is injective, just follows from the condition, and the first n minus p minus 1 circle is incompressible, follows the fact that every circle in this cube, it has a dual hypersurface, such that the circle components intersect the hypersurface only once. And this property does not affect it if we doing the generalized kinetic sign on TK. Yes, in the case 2, if the inclusion map is non-zero, then we notice that the hypersurface homology to Tn minus k minus 1 cross dk, namely this shadowed hypersurface, are Xungyao shrink manifold. Yes, and we won't focus on this case. In this talk, and we just focus on the third case. And in the first case, we just reduced to the situation that a manifold has some incompressible torus. So now we mention the PS obstruction in this situation. I will call it PSC obstruction from incompressible hypersurface. And the early result is the 3-dimensional case is dealt with by Xungyao. They prove that if sigma is orientable closed surface with positive genus, and M is a 3-manifold such that there is a map from sigma to M, such that the inclusion map between fundamental groups is injected, then M does not admit any complete PSC metric. And this result is generalized by Gromov and Lawson in their 83 paper. They prove their statement is conversely, but they say things in the same philosophy. Like the statement says if G is compact Riemannian manifold with polyscalar curvature and mean convex boundary, and assume the boundary is enlargeable and spherical, or it admits non-zero map to such manifold, then the inclusion map between fundamental group of the boundary and the fundamental group of the whole space cannot be injected. Here, a enlargeable and spherical is just is for the following purpose. The enlargeable just would like to ensure the following property, namely, if a manifold admits a non-zero degree map to the boundary, then it does not admit PSC metric. And a spherical is for the following purpose, namely, if you have a manifold, its fundamental group to the fundamental group of the boundary has a homomorphism, then we can always find a map from N to the boundary, such that the induced map on fundamental group is just the map F. Yeah, and then we just follow the idea of Gromov loss, and we just take because all they needed is these two properties, so we just formulate a particular class. The class C is defined to be orientable closed a spherical manifold sigma, such that the manifold with non-zero degree 2 sigma admits no PSC metric. and there are some non-examples. For example, we know orientable closed strict manifold with dimension less than 6 is belong to the class C. This is proved recently by Chen and Gromov. And you can always you can also see orientable closed manifold with non-partial sectional curvature also belong to the class C. Yeah. Of course, for I know, okay, this needs the dimension restriction. I mean, that's dimension should be less than 9 because I don't know if a non-spin manifold admits a non-zero degree map to such manifolds cannot admit PSE matrix. I don't know that. So for safety, we'll limit to the case where dimension is less than 9. Yeah, with the definition of the class C, then we can state our second main theorem B. Say that Fm is a manifold associated continuous map from sigma to M, such that the inclusion map between fundamental group is injective. Here, sigma belongs to the class C, or sigma having non-zero degree map to such manifold. Then M admits no complete PSE matrix.
Jintian, so in the non-example you were mentioning in the second case, I think the dimension restriction is not necessary.
Oh, this
Yeah,
dimension.
if you assume non-positive sectional curvature, because then you can deal with it using index theory method.
I'm not sure because in my definition of class C, I needed to guarantee every manifold admits non-zero degree map to this manifold has of obstruction for positive scalar curvature. Because yes, I'm not just require itself.
Okay, I see.
Yeah,
I see. Okay, thank you.
Yeah, if itself, I know there is no dimension restriction there. Yes, here I do a remark. We don't. There is some. Oh, sure. I do a remark. Actually, we don't need to require the inclusion map to be injective. In some case, if sigma is some manifold that admits non-zero degree map F to some manifold sigma 0 in the class C, then we just need to require the kernel of the inclusion map I is belongs to the kernel of F star. F is here the non-zero degree map. This condition allows part of Taiwan maps to 0. And this fact will use to in our argument will use to deal with the possible non-embedded case for sigma. Since sigma is only a map into M, it's not an embedded hypersurface in M. And then we would like to use the survival method, and we need to start with the embedded hypersurface. And I just say the relative incompressible case, it can be used to deal with the non-embedded case of sigma. Yes. And in the last part, I'll talk about the application of our party mass theorems, and this is this has overlap with what just talked by Yu Guang. So I just skim this part quickly. And the original, the Brown mass is only defined for complex manifold with spherical boundary, and moreover, this spherical boundary need to have positive Gaussian curvature. In this case, the boundary can be embedded to the Euclidean space, so we can calculate the difference between total mean curvature in omega and the total mean curvature in the Euclidean space. So it seems limited. And it's well-known work. Xi Tan proves the non-negativity of the Brown mass in the case when the boundary is mean convex. This and currently we don't know whether the mean convex is technical or not, but it's just prove the non-negativity of Brown mass in some mean convex regions. Yes. Oh, as I mentioned, okay, the definition of this is limited. So Mantelidis Miao would like to generalize this, to generalize Brown mass, and their plan like this. They first introduce admittable fill-in. If given a connected closed surface, then we just define the admittable fill-in to be a complex manifold such that the boundary is isometric to the given surface. The scalar curvature is non-negative, and technically we need to require the boundary is mean convex. And the definition of Mantelidis is given like this. I just take the supremum of total mean curvature among all the admittable fill-ins, and I denote this quantity by lambda. Then for some omega g, the generalized Brown mass can be defined to be this lambda minus the total mean curvature in omega. Yes, of course, this definition makes sense only when the lambda invariant is finite. So we care about the finiteness of the lambda invariant. And in Mantelidis and Miao's work, they verify the finiteness of lambda invariant for arbitrary smooth metric on S2, while for surface other than S2, and we don't know whether lambda invariant is finite. That's their work. And as an application of our polymath theorem, we can show that if G is a flat metric of T2, then we know the lambda invariant of this flat torus is finite. And furthermore, if the flat torus splits as the product of two circles, then we can calculate the precise value of the lambda invariant. Yes. And here I would like to do a remark. Just as in Mantelidis Miao's work, it may be possible to prove the lambda invariant of a torus is finite through proving some polymath theorem with incompressible condition for locally asymptotically hyperbolic manifold. I think this may be possible to at least, okay, to finish the proof of finiteness of lambda invariant for torus in the torus case. Gromov has a more general conjecture. He says if you have any manifold omega g that with the condition 1 and 2, then the total mean curvature should be bounded about by some universal constant depending on the sigma and G sigma. And this conjecture is widely open. Okay, the issue is we don't know whether the mean convex can be removed in incidence result. Yes, we don't have an argument which can get rid of the mean convex requirement. Yes, this is just what we do in our picture. And the next part is about proof. And I will just mention the proof of theorem B, since the reduction is from party mass theorem to obstruction problem is almost standard. So I just to say how to prove theorem B, because theorem B is, it says if a manifold has an incompressible hypersurface sigma in the class C, such that the inclusion between fundamental group is injected, then M admits no complete PS matrix. And this proof roughly follows the argument by Gromov and Lawson in their work. But we just, for simplicity, we just deal with the case sigma belong to the class C. And actually, the latter one is similar. First, we just pass to a curve of M, such that the fundamental of this curve is isometric to the fundamental of sigma. Then since sigma is a spherical, then we can find a map from M tilde, the cover, to sigma, such that this composed map is homotopy to identity. Okay, use picture, it looks like this. If we imagine sigma is a hypersurface in M tilde, then M tilde has a compressed map to sigma. And when sigma is an embedding, then we know sigma must separate. Since the existence of this compressed map, we know, okay, sigma is homotopically non-trivial. And we can argue to show that actually sigma separates them into two unbounded parts. Then we can use the soap bubble argument. We can find a stable soap bubble. And the stable soap bubble is very similar to stable minimal hypersurface. So from the party of scalar curvature on M tilde, we can find a party of scalar curvature metric on this stable soap bubble. While this soap bubble is homologous to sigma, and the compressive map tells us this soap bubble allow non-zero degree map to sigma, while sigma is belong to the class C. So it's for the soap bubble cannot admit any party of scalar curvature metric, and this gives a contradiction. And for the non-embedded case, we just find since sigma represents a non-trivial homology class in N minus one, in Hn minus one, so we can find an embedded hypersurface sigma tilde homology to sigma, and then we just take one of its components such that the compressive map limited to sigma 0 tilde. It has non-zero degree. Then we have this commutative diagram. And in this commutative diagram, we know kernel I tilde belongs to kernel F tilde. So this is just reduced to the relative incompressible case. And we complete the proof. And the rest thing is standard. Okay, the reduction from party mass theorem to obstruction problem is that follows Schunel's argument. We just prove density theorem, and we use the Banning argument to finally define the infinity to be the model space. And then I think here you are well known, so I didn't focus on this. Yeah, yes, sir. And I just want to mention the rigidity case. Okay, why we need an extra condition in the second case. This is because when we have proved the party mass theorem, then we can see if the given metric has non-negative scalar curvature and the mass is 0, then the metric must be receive flat. And in the first case, we can lift to its universal covering, and the injectivity guarantees that the end is lifted entirely. So the universal covering will be a receive flat manifold, which has the end asymptotical to the Euclidean space. So in this case, we can just use the Bischoff-Gromov-Wallon comparison. And in the second case, since we only know the inclusion map is not 0, we cannot lift the end entirely. In this case, we just use the Bochner technique. We try to find enough harmonic one form, and we successfully find enough harmonic one form, and use harmonic one form satisfies the following relationship. And since the mass on the right hand side is 0, then we know all of these harmonic one form is parallel, and we can show the splitting of the manifold. This is the difference between these two cases, and I don't know whether this is conditions is technical. Yes. Let me see. I would like to say, okay, the proof of theorem A2
so maybe because we're over time.
Yeah, I'm over time. Sorry.
Yes. Do you want to make a conclusive statement, and then maybe some people have to leave, but then we can let you talk a little more.
Yeah. I just would like to say the proof of theorem A2 and the proof of theorem C just use the quasi-spherical metric method, just as in the Chen's paper. So the proof of theorem C, we just follow Chen's work, and we flow the domain to be an asymptotically conical manifold, and use the Kohn angle estimate in that case. So it is almost standard, I think. So I just stop here. We can, yes, I just stop here.